Oh, there we go. Welcome back from spring break. This is the first class after spring break in real time. Did everybody have a good break? Reasonably so? Did everybody use break for catching up? That's what I usually do. Yeah, reasonably so. Well, we are mostly here now at the bottom side of spring break, starting the second half of the semester, because that's what spring break always signals. Mostly going to be working in Chapter 8, although it probably doesn't exactly look like that from the agenda, because what I'm writing is project management again, and that's Chapter 7, not Chapter 8. The reason I'm writing it again is before spring break, or in the last episode if you are video binging on MGO302, right before an EQS module, we had been talking about a PERT problem, but I said, you know what, we're going to skip this one item and write. We will come back to it because I wanted to have plenty of time to talk about Gantt charts. So we'll do that in the first part. Chapter 8 is location planning. So we'll talk about basic issues because that's what's at the front part of the book. We'll talk about cost volume analysis. And I think you'll like that because it should seem really, really familiar. If that phrase doesn't, the actual underlying methodology, wait a minute, we've done that before. Okay, so in real time, right now most of the class is finished. I'm looking at that reminder that Native Son is due by tomorrow midnight on the Buffalo calendar. And a personal congratulations to most of the class. At this moment, it's like 71% of the class is completely finished with full credit. So those of you who aren't, right, as I'm talking in real time, there's still somewhat less than 48 hours. Now, speaking of that, and sort of speaking of recent developments in real time, our second exam is coming up next week. Right? Yeah, okay, everybody knows that. Next Friday. All right, so that means that not this class, because this is the Tuesday, but Thursday we'll look at the exam study guidelines, because we usually do that about 1 week before the exam. So if you like to get a sneak peek, if you like to look ahead, I will probably post those on this Wednesday if you want to look later on UB Learns, the study guidelines. I'm wondering if anybody noticed, because it went up really fairly late in spring break, but some other things have already appeared. If you want to go to UB Learns right now, I just wanted to quickly point something out. In the first part of spring break, I knew enough about the exam manuscripts to go ahead and create the super multiple choice sheet. So the super multiple choice kit for the second exam is available right now. Including generated some more of those crossword puzzles if you like those. So that's here. And this just went up late on Sunday, I think it was. This is, inside this folder, is a demo project validation quiz that will be handed out. The one-page quiz will be handed out with your second exam. Not only that, there's 2 documents in that folder. One of them is a demo quiz. It's showing you kind of similar to super multiple choice exactly what the sheet looks like. The other document is absolutely all questions that could possibly be selected at random because it's 10 true-false questions. The other document in there is the question bank. It is the complete list of all the questions that could possibly be selected at random to be among the 10 that would be on the actual piece of paper that you were handed that night. So that is sitting out there right now. On Thursday, we'll talk a little bit more about strategizing, getting ready for the exam. I just wanted to alert you to its presence right now in case you wanted to go look before then. Now, let me think. Before spring break, wow. What were we doing? Well, it seems like we were up to no page 67, sort of. Remember, we'd skipped and worked ahead on Gantt charts. We had been working on this problem, right? It's a PERT problem. I turned the page here in my notebook, and it's blank, but that's where you drew. And so I sketched it again. Remember this? I did this on the board. Let's see if we can get that in. There we go. We sketched the network for that small problem. We did the early start, early finish, late start, late finish times. Again, I was working on the board originally last time. And we came to this conclusion, and you can see that I jotted it down here, that the expected completion time of the project was 27 weeks. And that That is the answer to that question. Yes, the expected completion time of the project is 27 weeks. And I do believe before we left for spring break, we even lingered on that number 27 for a little bit to talk about risk. Because we noted that if you report that as your completion time, there's at least some possibility that you will be made a liar. Because you don't actually know how long each one of those tasks is going to take. That's how the whole problem started out. You didn't know exactly how long each one of the tasks was going to take, so you got those three estimates, the optimistic, the most likely, and the pessimistic. And it's always possible that if one or more of them actually turn out to be more the pessimistic time, it could take considerably longer than 27 weeks. Oh, all right. Now, at that point, we said, oh, okay, good to know. And then we skipped ahead to Gantt charts. Now, I want to come back and talk about calculating risk. The risk of, for instance, reporting 27 weeks. What's the risk that you'll be made a liar? What's the risk that you'll have to pay a late penalty because, in fact, it didn't take that long? Oh, all right. This is the other part of PERT that is different from CPM. Remember at the beginning we said, PERT and CPM, the graduation problem and this little movie problem, are 80% the same thing. All that is the same there. PERT's got a little bit of extra at the beginning because it's got that business about I'm not sure how long the durations are, so I get the three estimates and I use the formulas to find the expected time. And it's got a little bit different at the end. It has an extra module for gauging the risk then at the end. We're to that point. We're to that extra module. All right, now, first let's just talk about practical reality. If you know that there's some chance that it might actually take longer than 27 weeks, and the venture capital company is on the phone and they want your estimate, they want your commitment of when you'll be finished with this movie so they'll start seeing revenue, what are you tempted to do? Are you going to tell them 27 weeks? I mean, let's just be practical. Probably not. I mean, it depends on the risk, but probably not. So practically speaking, what are you going to do? You're going to pad that number a little bit, right? And this is the issue. Yeah, okay, just practically speaking, let's probably not tell them exactly that. Let's pad it a little bit, but how much? All right, well, PERT doesn't tell you exactly how much to pad it by, but it does tell you what the risk is associated with any number that you come up with. All right, so I'm going to propose a number. I'm going to say, you know what? I've actually seen this movie before, so to speak, and I know how it ends. 27 weeks is quite risky. Why don't we tell them 29? Okay, so I'm creating a deadline, and I'm reporting it to the venture capitalists that we're pretty confident that we'll be done in 29 weeks. What is the actual risk, though, that we will be able to make that deadline? What is the actual risk that we will overrun that deadline? All right. We drew this network. It consists of all of these tasks. Here's the thing about PERT. Ultimately, this methodology doesn't see your network as a bunch of activities. That's what we're looking at here. That's how we see it. It sees your network as a set of paths. Did everybody hear that? It sees your network as a set of paths. You say, what? Why? Because it sees the problem of getting done within 29 weeks as the problem of getting threaded through each and every one of those paths in 29 weeks. Because yes, the project's not completed until you've successfully threaded your way through each one of those paths and reached the end, the finish line. So the only way to gauge the risk of the whole project being done within 29 weeks is to break it down into its paths and figure out the risk associated with each one of the paths. That's how PERT works. Now, on the next page, there's a little empty diagram that's actually meant to mimic something that's also for a different problem illustrated in your book. Let's take a look at this. Let me find a highlighter pen. Notice first that this diagram is referring to the three paths. Remember, any route from start to end, ACE, AD, ABE, or excuse me, BE. The 3 pass through that network. Okay, now, the first path through the network, path AD, first off, I'll just tell you this, and then I'll defend my statement. The expected length of that path is 26 weeks. And according to the RAND group that invented this technique, the actual outcomes of completing task A, then completing task D, the actual outcomes, how long it takes, is normally distributed. That's what I was trying to sketch here. And notice that I made my normal distribution start and end at, you can see there's already hatch marks on the page. What are those hatch marks? They're essentially 3 standard deviations from the mean, because that kind of defines the spread of a normal distribution. And I could make those in advance because I happened to know this fact, that not only is the mean of that distribution 26 weeks, but the variance of that distribution is 2.778. And you go, wait, how did you know that? Okay, I'll tell you in a second. But for now, let's just get the 3 normal distributions that represent everything that could go wrong or right with the 3 paths sketched. ACE, the center is really similar. You can see that the spread is larger because the variance, the numerical expression of the misbehavior around the mean, is 3.96. I'll tell you where I got that in a second. And then over here, path BE is all the way to the left because if you look, the expected time for B is 4 and the expected time for E is 3 weeks. That only adds up to 7. We think that whatever happens on that particular path, the average outcome is going to be 7 weeks. I mean, it's pretty short, although the variance is 1.37. This is not a mandatory step in assessing the risk of 29 weeks, but this is a vision of the underlying philosophy of PERT. This is how PERT sees this project. Now, each one of these probability distributions is meant to represent every possible thing that could go on concerning that particular path, how long it would take to get through the whole path, right? Where any probability distribution is the highest, that's what we expect. That's in this case, on average. In the case of the, wait a minute, ACE, remember from last time, was the critical path, and that's what gives us the 27 weeks that we're kind of scared of. And, but how did I know this? How did I know how to sketch it where 3 standard deviations were from the mean? Where did I get this fact that the variance in the path was, for instance, 3.96? Wait a minute, why am I drawing normal distributions? Okay, this is the underlying theory. Remember that PERT only sees your project as paths, and it's looking at this one path, like ACE. You might recall all the way from before spring break, we said, oh, those formulas for the expected time of a project, they're based on a beta distribution representing the uncertainty concerning the task, a beta distribution representing the probability of any possible outcome with that task. Right, that's where we got those formulas. Okay, so there's this little beta distribution, and it represents what will happen with A, how long A will be. The path is the result of sort of a necklace of 3 beta distributions, one for A, one for C, and one for E. That doesn't look all that skewed. Remember, the beta distribution is the lopsided one. Okay, that was all before spring break. That was concerning just the tasks. Now I said, oh, you know what? We're going to draw the probability distribution associated with the path. And now I'm drawing normal distributions. Does anybody remember the central limit theorem? I'm trying to draw a normal distribution here. Normal. A nice, symmetrical bell-shaped curve, not a squashed, lopsided beta distribution. I do believe it's one of the keywords, thumbnails at the bottom of one of these pages. Yeah, the central limit theorem. Okay, you can have random variables, and they're all misbehaving in some certain special custom way, like a beta distribution. But if you're threading them together, you're like adding up their outcomes, and it's the outcome that you're concerned about, not their individual misbehavior. The outcome is going to converge to a normal distribution. That's the central limit theorem. All their noise will basically start to add up to a normal distribution, and that's our justification for gauging the risk in each one of these paths by using a normal distribution and not going back to that little beta distribution that we started with that gave us those formulas that we need for PERT analysis. You say, well, yeah, okay, fine. But I don't get, like, for the 3 normal distributions, where did you get the numbers? Well, first off, like if you're talking about ACE, you know, every normal distribution has a center, it has a mean. Mu is typically the abbreviation for that. For ACE, it was 27 weeks. Oh, the center, the expected value of the path, is the sum of the expected values of the activities. That's just logical. If you expect this one's going to take a certain amount of time, this one's going to take a certain amount of time, and this one's going to take a certain amount of time, the length of the path, you add them up, that's the center of the distribution. At this point, what may be a little bit more mysterious is, where did I get the variance? I was telling you with confidence that the numerical expression for the degree of spread here, misbehavior, around that center is 3.96. Where did I get that? Okay, here's a principle we just have to remember. Just as the expected length of the path is the sum of the expected lengths of the tasks, the variance in the path is the sum of the variances of the individual tasks on that path. Before spring break, before we even drew the network, remember, we started with this data, and I said, oh, well, you know, we don't actually use these estimates directly. We put them into this formula, and that's where we get the expected times, and then we do our early start, early finish, late start, late finish times. We were using these numbers. But wait a minute, we also made this other column, and I said, we're not really going to use it right now, but it's go ahead and handy at this point to calculate the variance in each task. That was this formula. Now to find the variance in path ACE, pull out A, pull out C, and pull out E. Oh, I copied down the wrong number, of which, you're probably wondering, how did you get 3.96? Sorry about that. It was 13.667. I was looking at the wrong number. These two are right. Variance is 1.89 here. That was the standard deviation, the square root of the variance. There we go. So the variance in a path is the sum of the variances along the path. For BE, it's just the sum of B and sum of E, so on and so forth. You say, okay, yeah, great. But what does this have to do with the deadline? It's time to add the deadline. I suggested 29 weeks. You can see that pre-printed. Why don't we add 2 more weeks? You could draw the deadline on this diagram, because see how these timelines, 29 would be about here? Draw it. Remember that the vision is, the belief is, that this represents every possible thing that could happen with path AD. Do you notice that we do nip a little bit of it off? A little bit of it extends beyond the deadline. That represents at least a small risk of missing deadline. Right there. Because, well, think about it, these numbers here, these are outcomes that all meet the deadline of 29 weeks. It's only over here where it reaches beyond the deadline, it's indicating a few things that could happen that actually do miss that deadline. Okay, now that's just path AD. You have to get through all of the paths, and you can see that, just sketching it, there is a significant risk of some kind. because quite a bit of that curve spills beyond the 29 weeks. Although with BE, it doesn't look, I don't think, it's not anywhere near the deadline. Okay, now, we just want to actually specifically answer the question, is it safe to tell them 29 weeks? There is apparently some sort of risk, but how much risk? Here's our belief. The degree of risk right now of telling the investors 29 weeks is basically the proportion of every possible thing that could happen that is betraying the deadline, that is beyond the deadline, or the portion of the curve that is reaching past the deadline. All right. Now wait. I wish I had a table that just told me that if I made a cut at 29 weeks, what portion of a normal curve would be to the left and what portion would be to the right, given that the curve had a center of 27 and a variance of, 13.667. I don't have any such reference. I can only kind of eyeball it and say, well, it looks like a fairly significant chunk, but I don't even know if my sketching is all that accurate. I don't have such a reference for a curve that has a center of 27 and a variance of 13.667. But I do have a reference for a normal curve that has a center of 0 and a variance of 1. Does anybody remember from multiple previous classes what a normal curve, what's the name of a normal curve that has a center of 0 and a variance of 1? It's just a particular, I'm pulling it out of the air. Mu equals 0, variance equals 1. That's your standard normal curve. Yes, you said, okay. Well, what good? We don't have any path here that its normal distribution looks anything like that. A center of 0 and a variance of 1. True, we don't. But we do have a table that does tell us that if you cut that curve at a certain point, exactly how much is to the left, exactly how much is to the right. That's what we need to know. And we do have a way of translating any curve into a standard normal curve. This is like MGQ201, MGQ301, and you probably even had it earlier in another class. Is this bringing back any memories? The idea of scoring, calculating a z-score. Here's our problem. It says we have to fill out this table. We didn't have to draw this. I was just trying to motivate the theory behind it. What we have to do is fill out this table. And this table wants a thing called a z-score. Oh, path z-score equals the deadline minus the path mean or expected value. Mean is just shorter to right, so I'm writing that. Divided by the path standard deviation. The idea of using a standard normal curve to gauge risk is one of the most popular generalizations in business analysis. So you have probably seen this as z equals x, the number I'm interested in, minus mu, the center of my curve, divided by the standard deviation in my curve. We're actually going to work with z values and z tables more than once in this class. You have seen it in other classes. Now, wait a minute. See, x is the number I'm interested in here is the deadline, 29. Mu, the center of my curve, that is the path mean or the path average. And the sigma is the path standard deviation. Oh, all right, so here we go. We have the 3 paths. We don't actually need the pictures. We just need the summary statistics. The path mean for AD is 26. For ACE, that was the critical path. That's the 27. And then BE is the short one, 29. The path variance, 2.778. Is this 13 or 15? Well, sorry about that. I know somebody is working along somewhere and going, wait a minute. This is 15.667. I hear angsty sighs in the audience. Sorry about that. I'm just getting back on track from spring break as well. But somebody could have shouted out, wait a minute, how do you add 2.778, 1.111, and then 1.778 and get 13 some odd? Isn't it going to be higher than that? Yeah, it's 15.667. But actually what caught me there was just my bad handwriting. This, 1.889. Resulting z-score, oh, wait a minute. Let's fill this out. I'm interested in the number 29, right? That's the deadline. Minus, if we're working on path AD, it's 26. So divided by the path standard deviation, what do I put there? So what should I write? Good, the square root of 2.778. Because the standard deviation is the square root of the variance. That's why the variance is sigma squared. And that's always something to remember, because in PERT, there's this pattern where what do? You always find the path variance. You cannot find the path standard deviation, even though I know that's what you need for the z-score, right? You find the path variance. Remember to take the square root to get the standard deviation, because, right, that's what you want for the z-score. Remember that there's no way, there's no shortcut. There's no way to directly find the path standard deviation. Find the variance and take the square root. Anyway, I'm saying, oh, yeah, you have to calculate this score. And it comes out to like 1.80. What am I supposed to do with that? Practically every business analysis textbook has one of these in the back. This is our textbook. It's a z-table. This is a standard normal curve. Z-tables everywhere. They come in different formats, but they always tell you in a cartoon across the top what it is that they are providing. This is telling me that if I look up a z-score, it's telling me how much of the curve is to the left, because that's what's highlighted in the cartoon. Oh, okay, and this is exactly what I want, but I have this 1.80, right, look up the first two digits here, 1.8, and then scoot over to finish it off, the third digit 0, which means we're right in here, 0.9641. I'm just reading the table, 0.9641, 0.9641, area from the table, 0.9641. Yeah. Remember that one? We don't have to draw it, but we said there's a slight, small risk of missing the deadline. What the table is telling us is there's a 96% probability of actually making the deadline. So, just logic, there's about a 4% chance of missing the deadline, and that's what we were seeing. There's a little bit of a risk of missing the deadline from path AD. Now, path ACE, 29 minus 27, we're just filling this out, divided by the square root of, right, 15.667 gets you 0.51. 0.51, look up the first two digits here, 0.5, and then finish it off with the third digit, 1. That's the column. It says 0.695. I got to remember that. 0.695. 0.695. There is a 69.5% chance, about a 69-70% chance of making the deadline if you're working through ACE. Oh, that's the chance of making the deadline, meaning there's about a 30% chance of not making the deadline. That's that big chunk that we could see in the illustration. With task BE, you can calculate the z-score. The deadline's still 29 minus 7. That's the length of that path, divided by, take the square root of 1.889, and you get this big number, 16.01. Now, you can go to the z-table if you need to, but the z-table doesn't go up any farther than a little bit more than 3. Yeah, and we do tend to use a shortcut in this type of analysis. If you get a z-score more than 3, just say, forget about it. 100% chance of making that deadline, right? The bigger the z-score, the less the risk of missing the deadline. If a z-score comes out bigger than 3, we tend to not pursue the detail. We say, you know what, we're not worried about that path. We're not worried about that path because we could see in the illustration that you don't have to draw that path's not anywhere near the deadline. Oh, okay. So what I have is the risk associated with each one of the paths. The ironic thing is, I only want to know the probability that the movie will be finished in 29 weeks. And I've got this fact here that if you look at its 3 paths, one of them has a 96% chance of being successfully completed within the deadline. One of them has a 69.5% chance, about a 70% chance of being completed by the deadline. And then one of them, we said, don't worry about that. That one will be completed by the deadline. Oh, that's nice. Those are the paths. This is actually the answer. This is what we want to know. But with the whole thing, right? What's the chance about the whole thing being done? Oh, we have to remember one other principle from PERT analysis. The belief that the risk associated with finishing the project by a deadline is the joint probability of completing all its paths by that deadline. Joint probability. Wait a minute, what was joint probability? There's these 3 different things. They each have a probability. The joint probability, the probability they'll all pay off, right? That each one of them will be okay, is their individual probabilities multiplied times each other. That's what joint probability is. One's got a probability of 96%, one's got a probability of 69.5%, one's got a probability of 100%. We want to multiply the probabilities times each other. That's the bottom line, the probability, or that's the belief that all 3 of them will be successful. So, from path AD, we have 0.9641. That was from the z-table. Times, from path ACE, we have 0.695. Times, from path BE, that's the one I said, forget about it. You can forget about it algebraically. It's 100% is a 1. This, when multiplied times each other, I get 69.005, or excuse me, 67. There we go. We're thinking about telling them 29 weeks. At 29 weeks, we have a 67% chance of actually making the deadline. Yeah?
If all the paths have individual parts?
Is it changed at all if all the paths have individual parts? Actually, what you're sensing is that there's a generalization here that in reality it's one of the criticisms of this technique. If they all have individual parts, like none of the paths crossed, right? Yeah. If none of the paths cross, we say that they're independent. We wouldn't that I just described to you, it wouldn't hurt us. These paths, some of them cross. They share certain elements. This is actually, in reality, a upper limit, so to speak, on the risk. The risk could be more because if something went wrong with one of them, it would affect more than one path. So this is just meant as a quick estimate, but what you're sensing is if they don't share things, and this is actually discussed in the textbook. We have to go through a more elaborate procedure. It shows you a simulation instead and explore, right, then what the true joint probability is because the paths are not independent. It's the degree to which your network is tangled, whether you should bother with that or not. Now, let's say that we have, I'm just saying for the sake of discussion, no, we're pretty confident with that, although we're remembering that that's really only an upper bound on the risk because these paths do cross 67%. We have a 67% chance of making the deadline. Remember, we're telling them 29 weeks. which means that what's the probability it'll take more than that? What's the probability that, like, if we agree to late penalties, we'll be paying a late penalty? It's still pretty substantial, right? It's basically we only have a 2/3 chance of making that 29-week deadline. We'd have even less if we reported the expected completion time of the project. And we have a 1/3 chance, basically, of not making even that deadline that's padded by 2 weeks. So what should we do? Does anybody want to pad it more? Yeah. I would be inclined to as well, but actually there's no definitive answer to that question in that we need to know what the risks are. We need to know about the situation. It will be your judgment as the project manager how much you want to pad it, what degree of risk you're comfortable with. Maybe this is like a very informal, casual situation, and we don't really care. It won't be so bad if we overrun the deadline by a week or two. So we're comfortable with this. We got a 2/3 chance of actually making it, and we're not all that concerned about overrunning the risk. Then we might say that. If we're looking at steep financial penalties, I would think that is too risky, right? We would pad it more. PERT only tells you, well, it estimates. It guesstimates basically what the risk is. You, as the project manager, have to decide what degree of risk you're willing to tolerate. Okay, that's a judgment call. That is a more complicated situation. But PERT will give you an estimate of what the risk is, given you decide some certain number. We'll just leave this one at 29. If you wanted to say, oh, no, well, you know what, maybe you should add another week. How about 30? You would just make another copy of this table. Except the z-scores are going to be somewhat different because you're going to use a 30 for the x for the deadline instead of a 29, and then do the multiplication and then see how much you benefited if you're comfortable with that. So PERT gives us a way of gauging the risk associated with the deadline. That's really the extra thing in PERT. Now, we've already been there, done that. There are some old exam questions before we start another chapter. Let me note, although these are always on UB Learns. Whoops, you can't see that. EBD, EDC. You can see this is a CPM problem, a really old one from an exam. I'd say it's a CPM problem because it's just got like one estimate of how long things will take. And let's see, and so then there's a problem here about a Gantt chart apparently. And if you want some quick practice, I know it does not look like it, but this is an example of what's known as a hot start PERT problem. This is actually a full-blown PERT problem. It's just a small one embedded in a story, but it is the exact same analysis we just stepped through. Any questions on that before we close that chapter out? Okay. Time for a change of topic. Turning the page to page 8, you see this graphic that I put in your notes. It says something about the basic issues of location planning. This graphic right here is, let's switch up the view. Not that, we don't need UV Learns again right now. But, as you can see from the thumbnail, whoops, no, go back. Not yet. It's this. It's just a different statement of this is the, in essence, equivalent graphic in your textbook. Okay, wait. We're starting this chapter called Location Planning and Logistics. So now what we're going to talk about is not the design of the facility, but where do you want to place it? Okay, so it is one of the last long-term strategic topics in operations because you do need to pick carefully. That is not a decision that once you commit to it, you can back out of very readily, right? Picking a location. All right, now, look around you at all major operations. Factories that you see, stores, the North Campus of the University of Buffalo. Here's the theory. I'm actually standing in front of a graphic that's meant to represent a theory. The theory is, if you ask yourself, Why did that wind up right there? Why did they decide to locate right there? Why, for instance, is the North Campus of the University of Buffalo in Amherst? It can be explained by three groups of factors. Notice both in your notes and in this graphic, there's three groups. Three groups of factors. Each group has a certain amount of influence over the decision. The first group is input-related location factors. Oh, okay, and you see some examples are listed in your notes. The facility might be there because it wants to be close to its inputs. The facility might be there because there are certain features about that exact location that are indigenous to the location itself, and it wants advantage of that. Or the facility might be there because it wants to be close to the market. There are certain issues associated with the outputs. Now, wait a minute, inputs, transformation process, outputs. I'm reaching all the way back to the first week of class. Yes, actually, ultimately, location planning, loosely speaking, theoretically, goes all the way back to the first part of class. Oh, now wait a minute. How is this graphic going to explain why something wound up where it did? The real issue is the degree of influence between the three groups, because they pull on the decision for the best location in different ways. You can see that if you look at, there's a very short scenario in your notes. It concerns two companies that made two very different decisions concerning facility layout for factories, or it's not facility layout, concerning facility location for factories, and has everything to do with the graphic. Okay, let's look at this. Oranges for orange juice and potatoes for potato chips are both grown in South Central Florida. Okay, I just happen to know that because I went to school in North Florida. Minute Maid built its orange juice plants in South Central Florida, but Frito-Lay scattered its potato chip plants all over the United States. Why? Now, you might be wondering, what is so significant about this particular instance in location planning? I want to point something out. Okay, I've actually drawn on something from personal experience. Sorry about that, but I went to school in North Florida, and like you, when I was in school, I did not have a lot of money. But I found a very affordable house to rent. It was very affordable because it was literally right next to the railroad tracks. And so 5 times a day, CSX, does anybody know what CSX is? Yeah, sometimes they recruit here on campus. They're a big logistics company, right? Railroads would go right by the kitchen window. And that is what I would see. The whole house would shake, and right in the kitchen window, you would see Frito-Lay, Frito-Lay, Frito-Lay. And then you'd see Minute Maid, Minute Maid, Minute Maid. And occasionally you'd see liquid sulfur, danger, liquid sulfur. And then you'd see Minute Maid, Minute Maid, Minute Maid. Liquid sulfur, we're not talking about that. But you also, in South Florida, apparently, they mine a lot of sulfur. The thing that bothered me is that the liquid sulfur, those rail cars were the exact same rail cars that the Minute Maid rail cars were. They were big tanker cars. Because, oh, wait a minute, because out my kitchen window, what I was seeing going by, Minute Maid, actually was orange juice in giant tanker cars. That they use the exact same tanker cars for liquid sulfur, and I know that they wouldn't mix them up, but that just sort of made me queasy. When I saw Frito-Lay, those weren't potato chips. Those were the potatoes going by. Oh, right, because the Minute Maid plant is in South Central Florida. The potato chips plants are everywhere. They're regional. Why? Now, first off, it's not just this is from personal experience. I want to point some things out. I've picked 2 products, this is kind of like the first week of class, that are extremely similar to each other in many, many ways. First off, you say, yeah, they're both food. Fine, they're both food. They're both standardized products, correct, like first week of class. They're both tangible products. They're both, being standardized products are fairly low-cost products that you as the consumer find in similar places, like you go to the supermarket to find them. Okay, yes, sir. Wait, the similarities continue. These products are intensely similar to each other. They're both manufactured by global brands. Minute Maid, right, I just got this off of Wikipedia. You find that worldwide. Does anybody know who Minute Maid is owned by?
Coke.
Yeah, Coke. Coca-Cola. Interesting similarities. Frito-Lay is a global brand. Does anybody happen to know the parent company of Frito-Lay? Pepsi. Yeah, so just more parallels between these two products, right? Their parent companies, Coke and Pepsi. Oh, wait. Both of these products, this I just clipped off of the web, but this is in the plant. They're taking in the oranges. Both of these products obviously are created by rendering a single input, a crop. Oranges, there they are going into the plant, versus potatoes. Now, interesting here. What are we actually looking at from somebody's cell phone? This is outside a potato chip plant. This isn't a rail car. It looks like this is actually a freight container from a truck trailer combination. But what's going on here is that it's being tipped up and emptied like a box. If you can picture that, right? All of the potatoes that are in it, like one big cardboard box, that's what this hydraulic jack is doing, is picking it up and dumping it. Okay, wow. Oh, wait a minute. Now, I keep stressing how these two things are so similar. Yes, the products are incredibly similar, except for one feature, and that's where did they choose to locate the facility that actually created the product. And those are two very, very different decisions. But I think now we're starting to see why just on that one dimension, these two very, very similar parent companies that own two very, very similar companies that create two very, very similar products made two very, very different decisions. All right, I said that location planning, there's these three categories. Think of the two outer ones, outputs versus inputs. On the input side, like oranges and potatoes, which of these two products crushes, rots, has a higher sugar content, has a higher fragility? Potatoes or oranges? Oranges by far. Oranges have a very high sugar content and a high water content, and that means that as an input, you need to be careful with them, right? You can't even pile them too high or they'll start to collapse under their own weight. Versus potatoes, as just an object in logistics, are very rugged. You can see that they're emptying the entire truck, letting them all fall out. Oh, okay. So on the input side, it's a lot trickier handling oranges than handling potatoes. Now, wait a minute. Output side. There's another side to this. On the output side, I was watching the output go by my kitchen window. They had loaded it into rail cars. It was orange juice concentrate. Actually, it's going to a bottler where they're going to put it in cans and bottles, but the product was made, right? So it's very convenient to carry once that product's made. What about potato chips? Yeah, if you see a Frito-Lay truck going down the road, like making deliveries, for a variety of stores, what is that truck mostly full of? Anybody have a sense of that? Air. There was a guy did a study in the UK, and I thought, I knew this, but I thought, wow. I didn't really appreciate the scale of it. This is a bag of potato chips. It is 86% air by volume, because in order to protect the far more fragile output, they puff the bags with air, right? It protects the contents. That means that this big pillowy bag, this is 86% air, and actually the underlying purpose of the study was to stress the fact that if we didn't do that, if we bought potato chips vacuum packed, because you could do that, that would protect them also. Can you picture that? We just draw out all of the air and they're protected by the tightly fitting plastic. Essentially, you could cut carbon emissions, all of the shipping by 80. You could take 86% of the Frito-Lay trucks off the road. Oh, wow, okay. So why don't we do that? I think because people wouldn't buy the potato chips, right, if they were flat packed like that. But nonetheless, this is highly inconvenient. Trucks have a high fixed cost. We are shipping something that's mostly air. Therefore, we don't want to be doing a lot of shipping, right? We want to minimize the shipping. This is an issue with the output side. That's why Frito-Lay and Minute Maid made two very different decisions. Minute Maid's decisions was driven by the inputs. They're what's fragile and tricky, so they put their plant right in the middle of the orange groves. Oh, that's what a lot of people call a product-oriented plant. I saw a survey of factories in North America, and it indicated that I think it was 58% of them, something like that. It was less than 60%, but it was more than half of them were product. Why did they wind up where they were? They're product-oriented plants. They're trying to be near the input. Oh, okay. Versus Frito-Lay. Frito-Lay has what we call market area plants. Frito-Lay puts its plants near the markets to minimize the handling of the outputs, right? It doesn't care about shipping the input long distance because that's easy, the potatoes. That same survey said like about, I think it was 38% of North American facilities, if you're looking at them, it's arguably market area. Why are they where they are? That's what they're trying to do. Those two numbers don't add up to 100%. They don't add up to 100% because there was a third category, right? The regional factors. Okay, a much smaller portion, but some facilities, the explanation is more specific to the region. For instance, oil refineries are not close to the market, and they're not close usually to the fields where they're extracting the oil. They tend to be somewhere in the center, like on coastlines. That's kind of specific to oil refining. So they say, oh, well, that's that third catch-all category. And I had started this whole discussion of, well, why did something wind up where it was, citing the North Campus of the University of Buffalo. Does anybody know why we're in Amherst? You think is it input oriented? What are the inputs?
A bunch of land that was cheap.
It was, yeah. Actually, I've heard different stories. There's a whole bunch of land that was cheap. I've heard different stories. Maybe urban myth. We never will know exactly why, but it was definitely that central category. If it was specific to the situation, specific to the spot. Yes, there was a bunch of cheap land in Amherst. It's not really, it doesn't influence ours, but it's starting to come out in the news in some of our other developments. For instance, tax breaks. If a region offers a tax break for the location of a facility, that's considered in that one. That might be the explanation for where it is, like Solar City. University of Buffalo, yeah, probably it was the land. And it's, anyway, this regional group, it's something that's specific to the spot. It doesn't really have to do with the product exactly, at least not the inputs, the outputs. It's got something to do with exactly where you are. You've got some kind of special offer, there's favorable taxes, but it has to do with the location itself. Okay. Then, is any questions or comments on that? All right. This is essentially the front end of Chapter 8. Then the chapter goes on and it talks about there's actually a lot of methodologies that you could use to pick a location. It talks about three models. The three why three? Because the three models reflect three different situations within the problem of location planning that you might be in. The first one, cost volume analysis, the first one we're going to talk about, I think that you will like once you realize, wait a minute, to a certain extent, 80% of it, I've done this before. Beyond simply strategizing about, loosely speaking, inputs and outputs, you're trying to pick a specific location. Something that might be useful is so-called cost versus volume analysis. You're usually talking about a production facility, although, again, it's not physics. That isn't a strict law. It might be easiest to learn it to picture a factory. Picture locating a factory, because this whole technique isn't going to be of any use to you unless you feel that this fits your situation. I'm trying to locate a factory. That's the easiest thing to picture. Though you can use this for a lot of stuff. I have to believe that most of, just broadly speaking, strategically speaking, the difficulty in different locations has to do with my fixed versus variable costs. Oh, man, we've talked about that before. You've had that in a ton of classes. Oh, okay, so most of what makes one location different from another, most of what makes my strategizing difficult is my fixed and my variable costs. Oh, fixed costs, costs that do not vary with activity level. I'm going to locate a factory. Right now, I don't know how busy it will be. I don't know if the product's going to be successful or not, right? I'm just thinking about what's the biggest fixed cost. It is a bill that you have to pay even if you wind up not even using the facility. Rent or mortgage. Land. Yes. Real estate. Yes. That's generally the lion's share of the issue of the real estate. There might be other ones, depending on, like, if you were talking about locating a clinic, maybe that involves a lot of professional salaried people, then they say, well, that's actually an example also of fixed costs. But we're getting kind of exotic. Franchise fees. If you're thinking about locating a facility, then you're going to have to pay, and you want to buy into a franchise. Franchise fees are an example of fixed costs, although they generally don't clutter up your location planning decision because unlike real estate, the franchise fee is not likely to vary between locations because it's what you're charged by the parent company. Anyway, okay. So you have these fixed costs, and you have, we talk about variable costs. Oh, right, the costs that vary with activity level. That could be utilities. That could be hourly labor. That could be the materials. When were we talking about this before? You guys remember? Look, it was like there was stuff like this on the first exam. You're in capacity planning. Oh, right, because that also goes along with location planning, right, and facility design. Capacity planning, fixed and variable costs. Yeah. Break even. Yeah. Cost versus volume analysis is actually a simpler version of break-even analysis. It's an adapted, simpler version of break-even analysis. It's got that same outlook on everything as everything boils down to fixed versus variable costs. You see there's a third bullet point up here. It says the facility has only one product. Just picture that. It makes like one thing. That's actually not a strict requirement in that most facilities produce a variety of products. You just have to be able to aggregate it into one kind of basic activity level. We're going to talk about that later in Chapter 11. Most facilities, even when they provide a diversity of products, you can aggregate it into some single activity level. Excuse me. Oh, all right. So, cost volume analysis is kind of like line balancing, and the easiest way to describe the technique is to simply walk through it. Cost volume analysis, what you begin with is a list of candidate locations. So there's like this example problem in your notes. Now, this may have been a lot of work in and of itself. If you were doing this type of study in reality, you would have to go out and identify what your candidates are because you need to know the fixed and the variable costs at each one of the locations. Because we said that's your obsession. That's what you think characterizes the difficulty in picking between them. Now, cost versus volume analysis has an easy case that isn't very realistic and then a more realistic case. Now, in the easy case, it says, suppose we know how much the facility is going to produce. Remember, we're picking a location. So we haven't even built the facility, let alone started to use it. But maybe we do know that we're building a facility that this doesn't provide a context. Just picture any product you want. And we know that the facility is going to produce 36,000 annually. We know the volume. These are the costs. In the easy cases, we also know the volume. It's easy because it's just logic. Our obsession is cost in this particular. So just think about it like a contest. Test each one of your candidates to see who costs the least. Let's see Charlotte. If we locate in Charlotte, we pay that monthly cost of $10,000. Plus, we pay $10 for each unit produced. That's what the variable cost is. So I want to say $10 times how much? So what's the number here for the volume? You're about to say 36,000. And I'm glad. Actually, this is good. Okay, don't write that. Like, I'm not writing it because I'm writing in ink. And I've already scratched through enough numbers today, right? I'm trying to draw, I'm saying this is actually pretty easy. I'm trying to draw, like, really the only thing that you might stumble on just so that you're alert for it. Why can't I write 36,000?
That's annual.
Yeah, because it's annual. Just be careful. When I wrote the 10,000 in ink, I committed myself to estimating the monthly cost of being in Charlotte, the monthly cost. And then I need the volume to figure out the monthly cost, right? But here's the problem. It's not really a problem. Yeah, the volume here is deliberately annually. So wait a minute. If I'm going to produce 36,000 annually, 36,000 divided by 12, what do I expect to produce each month? Yeah, that's the number that I would want to use for my computations. I just want to figure out what it costs each month to be in Charlotte. So I get 40,000 monthly. We could do this over again and write 36,000 here, but I would not want to write 10,000 here, right? I would want the annual fixed cost of being in Charlotte. I would want to multiply that by 12. And then if we did that for all three of them, that would work too. We just don't want to mix them. So just be careful about that. Don't mix them. All right, now, maybe I want to be in Boston, where it's one of the most expensive cities in the United States for real estate. So notice it has a really high fixed cost. But it is, of the three that are mentioned, the only port. So it's got nice low variable costs. $2 for, now this would be the same volume. 3,000, Boston would work out to be worth it, even though it has high fixed costs. It's better than Charlotte. It costs less than Charlotte. We know that we would prefer Boston. That's just the logic over Charlotte. We're not done until we've checked all three of them. Omaha, just test it. 20,000 plus 5 times 3,000 equals, wait a minute. In my notes, I get 35,000. And we have solved this problem. Now, here's all my scratch work. We've solved this problem. What is the answer? Omaha. Yes, remember, the only thing we're trying to do is pick a location. Make a thoughtful choice of a location. And our choice would be Omaha because it's the lowest cost. Okay. Now, we can only reason through this problem of picking one of these three cities because somebody told us the volume. That's not very realistic, at least within bounds, because we're picking a location. Again, we haven't even opened the facility. So let's take that away, where we're not sure what the annual volume will be. What is it then that we're supposed to do, because we don't have any number to put here? The best thing that you can do, if that is a better descriptor of your situation, and that is actually what's the most common, is to illustrate your dilemma. You're trying to pick between these three things based on cost, right? And you don't know, though, what the volume is, and the volume drives the cost. So graph it. That, if you turn the page, it says is not the not so easy case. It's not difficult, right? But it's not as easy. We're not certain about the production level. So I want to illustrate what it is that I'm not certain about. Now, we need a little context here. The problem is we don't know what monthly production will be. So I'm going to appoint the x-axis to represent every possible outcome from, it turns out that we wind up producing nothing, to a good scale for this problem. In my notes, I counted every 5 grid squares and made it an increment of 1,000. Like here we are producing 1,000 a month, 5 more. Here's 2,000. Here's that 3,000 that we were looking at on the page before. 4,000. They were really busy, even busier. That's good enough there. Now, this is what we're not certain about. And this is an economic argument. So what is the vertical axis? This is cost. Because this is what we're basing our decision on. Now, a good scale here, what I have in my notes is, again, count every 5 grid squares, grid squared, but make it increments of 10,000 for monthly cost. So let's see, 1, 2, 3, 4, 5, there's 20. There's 30. There's 40. All right, now, we have laid out the setting. What is it that we're actually going to illustrate? The locations. We're going to illustrate the locations. Let's begin with the first location, Charlotte. I want to illustrate the monthly cost of being in Charlotte, essentially over a whole just range of production levels. Now, one of our underlying assumptions, and sometimes this is tricky in reality, but we'll just go with it, is that we have linear variable costs. That means that if I were to chart every possible level of cost in Charlotte, you know, given we were using different numbers here, it's going to describe a straight line. Oh, which means that I don't have to test a bunch of production levels, because if I can find 2 points on a straight line, I have found the line, right? One of those 2 points is always super easy to find. This is my favorite shortcut. Okay, thought exercise. We locate in Charlotte, and it turns out we don't produce anything. Production volume is 0. What will be our monthly cost? 10,000. It's just the fixed cost, right? Chart that, because that's what this represents right here. Here's us doing nothing every month. If you're in Charlotte, that's what you're paying. Now, I just need to know what the exact monthly cost of Charlotte would be for some other production level, and then I'd have my other point. You could test 1,000 or 4,000 if you wanted to, but actually we have a reading over here, right? From our work before, we had determined that if the production level was 3,000, the monthly cost would be 40,000. Just chart that. This represents monthly production of 3,000. If you're in Charlotte, that's what you're paying, 40,000. If I have 2 points, I found the line. The height of this line on that money scale represents the cost of being in Charlotte, North Carolina, one of the fastest growing cities in the United States, over all different production levels. Okay. How does that stack up against our other candidates? Well, who's next? Boston? Let's see. If I locate in Boston, my favorite shortcut, and I refuse to produce anything, I will still pay, remember it had the steep fixed cost, $30,000 a month? Then to find one other point, I happen to know already that if you produce $3,000 a month, you pay $36,000. $3,000 a month. There's the 30,000. Let's see. So 36,000 would be right there. Wait a minute. Connect these 2 points. I have a lot flatter line. This is the cost of being in Boston over a wide variety of production levels. And I already see that there is a certain amount of production, small numbers, where, wait a minute, Charlotte is lower, but there is a certain point in which it pays off to be in Boston, the higher numbers, because that line is so flat, right, because it had that really low variable cost. Anyway, can't really start strategizing until all 3 of them are here. Third one, okay, if you locate in Omaha, Nebraska, and you don't do anything, you still pay $20,000. That's right there, right in the middle. That's Omaha, right in the middle of North America. If you produce $3,000 a month, Then it costs you 35,000, so that's going to be right below Boston's second point, splitting that. If you found 2 points, you found the line. So Omaha's kind of this in-between thing. Every time you draw a line in this type of analysis, here's my recommendation. Label it immediately. The reason is that you're going to go back later and you're going to want to know which line is which. So never leave the line until you label it. All right, now let me back out the visualizer just a little bit. You can take a look at this. Okay. Oh, before I talk about it, though, I want to point something out. I've finished graphing the cost function, essentially, of each of the candidate cities. I'm taking a highlighter pen, and I am highlighting, notice, the lowest line in each case from left to right. Right? Basically, don't let the highlighter cross any lines. This is what we like to call, in this type of analysis, is the efficient frontier. But, more practically speaking, what is it to you? The lowest line on the graph would be the preferred location in that instance, right? Because it's all about lower cost, lower cost, lower cost. So I'm highlighting the fact that, right, if you were producing only small amounts, the lowest line belongs to Charlotte. That's why it's important to label them as you draw them so you don't get them mixed up, which means that you'd want to be in Charlotte, in fact, if you were only going to produce smaller amounts. There is this zone in here in which this line, Omaha, is the lowest, like this mid-range, and what that's indicating is that, right, it would be the preferred location right in that band. And matter of fact, 3,000 is included in there. That's why we picked it when that was specifically our volume. Although there is some point that if you ramped volume up enough, you would start preferring Boston despite the outrageous real estate costs, because that's where the low variable costs would start to pay off. Oh, all right, so we've created a visual tool for, we still have to basically pick one of these three locations. What we're seeing is, and what the tool is clarifying, is that each has its own virtues under certain situations. Charlotte is preferred here, and then there's a point that it stops being preferred, and Omaha starts being preferred, but not forever, because if production is going to be high enough to pay down that big fixed cost, Boston would be preferred. Now notice where I put the border lines? Right where one tips over the other and takes over as the lowest cost. I am highlighting those points in particular. Just that one right there and that one right there. Not everywhere that a line crosses, but just along this efficient frontier. Important vocabulary term, point of indifference. It is known as a point of indifference. It's the borderline between where you stop preferring one candidate and you start preferring the other one. Now, wait, how is this going to help us pick Charlotte, Omaha, or Boston? Oh, well, we said we didn't know what volume it was. True, but we probably know somebody that knows something about the situation. Now we have a tool to try to draw more information out of them. Because maybe we approach the guys in marketing and we say, what do you think our monthly volume is going to be? What do you think sales are going to be? And they might say, oh, we can't tell you right now. It's too uncertain. And so we say, well, I don't know. Do you think it's going to be more than 3,000? They say, oh, what are you talking about, 3,000? Are you crazy? This is like, 500 or 1,000, but we can't tell you exactly, right? 3,000, that's outrageous. Oh, they don't have to tell us exactly. If their reaction to 3,000 is, that's outrageous, you're talking about things that are in the hundreds, they don't have to tell us an exact number for monthly production, because if it's going to be like in the hundreds, where would you want to be? Charlotte. Or if their reaction to, what do you mean 3,000? You guys got to get ready. It's going to be at least 5,000. And we can't tell you, man, it may be way more than that. Oh, you don't have to tell us. If you're pretty confident it's going to be at least 5,000, we definitely know where we want to be. Where do we want to be? Boston. Yes, that's how you use this. So the only other thing that we could do, perhaps, to improve on this tool just a little bit is just be a little bit more precise about when you quit on one location and when you start preferring another one, right? Because I was picking pretty easy things that were at the extremes. Oh, well, that's actually easy enough to do. You just find the points of indifference. Because where you stop preferring something, like Charlotte, and start preferring something else, like Omaha, is right where the two lines cross, correct? Each of those lines represents costs, so that's the point of volume of which the cost is exactly the same at each location. That's why it's called a point of indifference. Is because if the volume happened to be, like here, it looks like it's about 2,000. If the monthly volume happened to be that number, you wouldn't care. The cost would be the same. You'd be indifferent. Oh, and once we realize that is what that means, you could reason out exactly what the points of indifference are. One of them is between Charlotte and Omaha, right? Now notice not every pair of candidate produces a point of indifference, but there's definitely one between Charlotte and Omaha. And I'm just asking myself, when is the cost at these two locations exactly the same? Well, I could just spell it out. The cost at Charlotte is $10,000 fixed plus $10 times every unit that we produce. And I'm just writing an X for unknown. When does that happen to be coincidentally exactly the same thing as the cost in Omaha? Which is $20,000 plus 5 times that same number. What number would make those exactly the same? Oh, well, now I can just solve for it. 5x equals 10,000. Oh, my freehand graph came out pretty good. The point of indifference between Charlotte and Omaha is 2,000. At 2,000 units every month, the cost would be exactly the same. Anything beyond that, 2001, 2002, technically you'd prefer Omaha. It would be less expensive. Below that, that's where Charlotte rules. You'd always pick Charlotte. The other one is between Boston and Omaha. Repeat this logic, except use the appropriate numbers for Charlotte and Omaha, and see if you can confirm my answer. I get that the point of indifference between Boston and Omaha algebraically is 3,333 1/3, which is sort of kind of freehand where it landed on my graph. Meaning at 3,333, you would prefer Omaha, and at 3,334 is a month is when you would start preferring Boston. And from 3,334 upwards to any number, theoretically, Boston is where we want to be, right? That is a high enough volume to make the high fixed cost worthwhile. You saw this before the first exam. Points of indifference. We said, oh yeah, this is basically an adapted, simpler form of break-even analysis. Do you remember break-even analysis? We were talking about American Steamship Company. And we had the two ships, the Sam Law and the American Century, and we're trying to figure out which one to pick. And I gave you a number, and I said at a certain number of tons, you wouldn't care which one of those two ships to send. I had calculated the point of indifference. That's where I got that number back when we were talking about Chapter 5. Okay, Well, this is a really nice stopping place. And then we'll just pick up with more location planning stuff on Thursday. Thanks.